So I'd like to look at the receiver structures for these different modulation formats, and in this case I'm talking again about coherent detection, where we assume that we have knowledge of the carrier phase, and that's because our solutions for the signal space, that these vectors are cosine and sine. This works for coherent detection because we know the phase offset, and I'll be talking later when we talk about non-coherent detection about why this wouldn't work for signals where we do not know the phase. But for now, we assume we know the phase, coherent detector, and we're going to look at what are the different receivers for different modulation formats. So remember, what are the challenges when we move from binary to M-ary? We need a receiver that's going to choose the right symbol. We could either use the map that maximizes the a posteriori probability, or the maximum likelihood that chooses the most likely symbol transmitted. So these two strategies are what determine the form of the receiver. And inside of the receiver, there'll be a decision algorithm. And they'll be slightly different between map and maximum likelihood just because of the a priori probability, whether it's present or not. But basically, the structure stays the same. Once we have the receiver, then we can ask the question, what is the performance of this receiver? And when we look at the analysis for the binary case, we'll be exploiting those results in order to do the analysis for the M-ary case. So to determine what the receivers look like, let's go back to our definitions. What is the strategies the receivers are taking? And for the map, of course, we have an expression where we have here the a priori probabilities, and this weighting is present for the map and for the maximum likelihood. The only difference is this weighting. So in this case, let's look at maximum likelihood. We're looking at the distance between the received symbol R in each one of the possible transmitted symbols, and we're trying to pick the symbol which is closest to the received one, which minimizes this separation. And we've talked about this earlier in the binary case. Well, actually, it wasn't even binary case. When we talked about signal space analysis, we looked at this and we discussed the correlator nature of the receivers. So remember, we said that the distance squared between two vectors we can write as the sum of the length squared of the two vectors less a term which is the inner product of these vectors, so the received vector with the symbol. And since the R is the same and across the minimization of our I, that really doesn't enter into it. And these blue things can be pre-computed, so they're not really part of the structure of the hardware of the receiver. What we have to calculate each time is this inner product, and this inner product is our correlator. So if we were going to look at a general format for the receiver, and again this is for coherent detection, we would take in the received signal and we would have several branches. In fact, we'd have M branches, one for each one of the symbols. And in each one, we would calculate this inner product. And we would get M different inner products, and we would find the optimal one by some decision stage. So I call this the decision algorithm. So the structure of the receiver is a bank of correlators. So what I want to say is there's a better way to do this, which we can see as we looked at different modulation formats. When would there be a better way to do it? It depends on the modulation format. For instance, suppose that there were fewer basis vectors than there are symbols. Let's take PSK, where there's always two-dimensional, no matter how many symbols there are. Or QAM modulation. It's always two-dimensional, no matter how many symbols are in the constellation. In that case, I can reduce the number of correlations I do to the number of basis vectors instead of the number of symbols. And I'll be showing you why that's the case. But this could be a huge reduction. For instance, we could have 64 QAM, which would require 64 different correlators. But if I use the basis vectors, it's always a two-dimensional space, so then there would just be two branches. So the hardware complexity would go way down. And of course, this is the way we do things. It's not the first way, it's the second way. And let's see how that works out. Well, if we go back, essentially we're trying to calculate the closest symbol. And here we said that that's equivalent to calculating the inner product. But if I want to find the closest symbol, well, one thing I can do is just look for the coordinates of the received signal, plot that coordinate, and then decide which region does it fall in. Does it fall to the left of the threshold line, to the right of the threshold line? You know, which region of the space does it fall into? And so then we just need the coordinates. And basically, these coordinates, we assume that we have the coordinates of the symbol, we know those already. So what's different is every time we receive one, we have to get new coordinates here. So basically these branches are simply calculating the coordinates of the received signal in the signal space. And then in the decision stage, in the logic stage, well then we exploit the previous information we have about the positions of each one of the symbols. And based on what we have here, we'll figure out which region the received signal fell in and make our decision based on that. So for MPSK, there's two branches. Again, what we call the in-phase and the quadrature, a sine and a cosine. And these sines and cosines assume that they're in phase with what was transmitted. That's why we call it coherent detection. MFSK, we can do the same coherent detection. However, in FSK, the dimension of the space is just equal to the number of symbols because each symbol is a basis vector because each one of these symbols is orthogonal. And so in this case, there's no savings. So if I used one method or another method, if I used a bank of correlators, or if I looked for the coordinates in signal space, I would have the same complexity receiver. So that tells me that I'm going to have a different strategy for FSK than I do for MPSK. And the same for QAM. In QAM, there's only two dimensions. It's only two branches. So in phase and quadrature are the solutions for the MPSK and for the QAM receivers, whereas for the FSK receivers, I'm going to have to use a branch of M. And this is true for any orthogonal modulation. FSK is the only one we're looking at now, but there are other orthogonal modulation formats we could use, and they all have this same characteristic. So here would be a summary of the FSK orthogonal modulation, in which case we're going to go ahead and do a correlation with each one of the symbols. But in the case of QAM and MPSK, there's just the two branches, and one's for a cosine, one's for a sine of the carrier, and we call this the in-phase and the quadrature branches. So we've seen the form of the receivers. Now let's look at what's going on in those logic boxes. What's going on, what's going on here in the decision stage? What are the decision algorithms that are going on with each one of the receivers? So here, determine the decision algorithm in the receiver for this M-ary case. And the idea in our decision algorithms is to try and reduce the complexity of the decision algorithm by working with our geometric interpretation in the signal space. It also gives us an ability to have an intuition for how the receiver works. So remember, I'm trying to choose the symbol, choose the symbol such that this distance between the received signal and the symbol is as small as possible. Making this as small as possible is equivalent to saying choose the nearest symbol. And if I want nearest symbol, instead of actually calculating what are this, taking the coordinates that I found for R and calculating this difference for each one of the symbols, that could be a costly calculation. But what I can do instead is just determine regions ahead of time, and then I can just ask the question, does R fall in this region or another region? And depending on which region I fall in, that's going to tell me which symbol I should choose. So let's look at an example. Here are three points. We chose an example with equal energy symbols. So the energies have equal energies. They fall on a circle, just to make this example a little easier to follow. And in what is the first step that we do? How do we choose the nearest symbol directly from the received vector? So I'm going to have this is my signal space, and I'm going to have the received vector. I'm going to know it's somewhere on this two-dimensional plane. And how would I make that decision? Well, the first thing I'm going to do is start plotting perpendicular bisectors between pairs of symbols. So I did it between S1 and S2. Now I look between S2 and S3. Then I look between S1 and S3. And I look at the intersection of all of these perpendicular bisectors. And I come up with this set of 3 regions. So when the received signal falls here in this sort of purple colored region, I'm going to choose symbol 1. If I fall in sort of this green region, I'm going to select symbol 2. And if I fall in this blue region, I'm going to select symbol 3. So there are 3 regions in the plane, and I'm going to calculate the coordinates. And if the coordinates of the received signal fall in one region, I make the decision on that symbol. So the answer, how to choose the nearest symbol directly from the vector received, is simply to have predefined regions and then decide whether it falls in that region. So let's take the case of MPSK, which is, of course, also an equal energy example. And in this case, the regions, here, let's look at this plot here. And here, this blue vector represents the received signal. And I could have calculated the distance to each one of my 8 symbols. But calculating the distance to each one of the symbols would have been computationally expensive. What I really want to do is just say, well, if it fell within a certain arc, then I know that that symbol should be chosen. So what I do is just calculate the 2 coordinates of r, which give me this vector, this blue vector. And instead of smooth, okay, here would be choosing the smallest one. But instead what I can do is I can do a slicer. And a slicer is, this is the regions. And now I have a slicer that shows all of the different regions. And now I say, oh, I fell in this region, so I'm going to choose this symbol here, the closest symbol. Not because I calculated the distance and it was the closest one, but because this I fell in this region, and this region is defined to go with that symbol. So slicer is one of the vocabulary we use for this approach.